Hey everyone! Today I want to discuss a type of single photon detector called a photomultiplier. It's actually the first video of two about single photon detection. In the current video I'll discuss the principle of operation, what you need to actually work with this device, and take a look at what detecting photons with a photomultiplier actually looks like. And in the next video we'll do a few follow-up experiments and look at the relationship between single photon detection and light coherence. So what is a photomultiplier? Well, it's a light detector based on the photoelectric effect. And for his explanation of the photoelectric effect, Albert Einstein received the 1921 Nobel Prize in Physics. When light within a specific frequency range is used to irradiate metals like, for example, cesium, the absorption of this light can promote the release of electrons from it. And if you do this in a vacuum and you have another electrode close by, you can actually measure the effect as a potential difference arising between the two electrodes, because the one that ejects electrons becomes more positively charged than the one that the electrons land on. However, this effect is only observed if the frequency of radiation is within the sensitivity range of the material. If the frequency is lower than a specific threshold value, no electrons are emitted at all, not even at very high intensity. So this indicates that the photoelectric effect is not about the total amount of energy supplied, but about the frequency of the radiation. Now, within the frequency range where photo-induced emission of electron occurs, we can observe that the maximum kinetic energy of the electrons ejected increases when we increase the frequency of the radiation. And it's this observation in combination with the frequency threshold that led Einstein to the conclusion that energy exchanged between light and matter not only occurs in discrete amounts, but also that the energy contained in these quanta is proportional to the frequency of the radiation. It's these energy quanta that we now generally refer to as photons. To detect the absorption of a single photon, we need a very sensitive device, and most everyday detectors of light, such as the CMOS sensors used in digital cameras, are not really sensitive enough to do this. But a photomultiplier can. When irradiated at very low intensities, it can detect the absorption of a single quantum of energy by a single electron. Now, as you may know, an electron is a pretty insignificant little thingy and represents an extremely small amount of mass and charge. And if we want to measure, let's say, a current equivalent to 1 electron per second, we need a device that can measure a current of 1.6 times 10 to the minus 19 amp, which is far below the sensitivity of most measurement devices. Even yours, Marco. So, to detect the emission of a single electron, we need to somehow amplify this minuscule current to a level that we can physically measure. And that is what happens in a photomultiplier. It's actually not multiplying photons, as the name suggests. It's about multiplying current. And it can convert the current representing a single electron to one that contains several million electrons in a very clever multi-stage amplification process. So let's take a look at how that works in an actual device. I will do this by discussing the photomultiplier type that I will do experiments with later in the video, which happens to be a Hamamatsu type R928. In essence, a photomultiplier is a special vacuum tube consisting of a quartz envelope with a high vacuum inside. It contains several electrodes, which are basically curved thin sheets of metal. They are electrically isolated from each other by these two white ceramic insulators, and each of these electrodes is electrically connected to an individual pin on the bottom side of the tube. This here is the sensitive side of the photomultiplier, where light can enter the device through a metal wire mesh. And I guess the best way now to explain how the device works is by means of a schematic cross-section showing you the internal layout in more detail. Here is a glass envelope with the high vacuum inside. This is the wire mesh through which light can enter the device, also called the focusing grid. Behind it is a photocathode, which is coated with a thin layer, usually consisting of a mixture of several low work function metals, like the cesium that was discussed in the photoelectric effect. And then there are, in this case, a total of 9 so-called dinodes, which can act as amplification stages. And the last component is the anode, which is a wire grid electrode looking sort of similar to the focusing grid. Each of these elements is placed at a specific voltage, and here you can see how these voltages are distributed over the different elements. In this particular configuration, the photocathode and the focusing grid are at minus 1000 volts with respect to ground. The diodes are placed at voltages of minus 900, minus 800, minus 700, etc. all the way to minus 100 volt for the last diode. And the anode grid here is basically at 0 volts because it is connected to ground by means of a resistor. So there are basically 10 different voltages needed to operate a tube, which is quite a lot. But we can generate these voltages relatively easily by using what is called a voltage divider circuit. So we start with a minus 1000 volts and 0 volts and use a set of 10 identical resistors to gradually bring down the voltage level in steps of 100 volts. And we then connect these intermediate voltages to the pins of the respective diodes. Now let's take a look at how a photomultiplier detects light. If radiation within the sensitivity range enters the device, its energy is absorbed by the photocathode. And this can eject electrons from the cathode material having a relatively low kinetic energy, generally in the order of only a few electron volts. Since there is a potential difference between the cathode and the first diode from negative to less negative, the field present will accelerate the electron towards the first diode, which thereby gains an additional kinetic energy of 100 electron volts. Now if you're wondering how fast an electron is moving that has a kinetic energy of 100 electron volts, we can quickly do a non-relativistic approximation and calculate that it's moving at about 6000 kilometers per second. Pretty fast actually from our perspective. With this kinetic energy gained, the electron hits the first diode and releases that 100 electron volts of energy on multiple other electrons in the material, which now also have sufficient energy to escape. And these secondary electrons then accelerate towards the second diode due to the local field. And here each secondary electron again releases multiple electrons and so on. And this process repeats with each diode, eventually leading to a true avalanche of electrons that reaches the final diode stage. Because the anode here is at the most favorable voltage for an electron to be at, most of these electrons end up on the anode grid. With all the electrons hitting the anode, charge builds up and current will start flowing to ground through the resistor, which we can now measure as a voltage over the resistor. And in this way, the initial emission of one single electron can result in a measurable current and a voltage pulse. A pulse because the electron avalanche will stop automatically once all the electrons have moved downfield. And after the whole show is over, the detector is ready for the next photon to be absorbed. Let's take a look at a few details on the datasheet of our particular photomultiplier. At an operating voltage of around minus 1000 volts, the gain of the device is around 10 million, which is a pretty impressive amplification factor. Effectively, it means that at every diode, an electron hitting the surface with 100 electron volts liberates about 6 secondary electrons on average. But due to the exponential growth in the number of electrons, this leads to 10 million electrons after only 9 amplification steps. Now 10 million electrons sounds like quite a lot, but it's actually still a very modest amount of charge, since it's only equivalent to 1.6 times 10 to the minus 12 coulomb. Still, it can be measured quite easily using an oscilloscope, mainly because this charge is released in a very short time interval. The datasheet shows that the total transit time of the electron avalanche through the photomultiplier is 22 nanoseconds, meaning that the whole amplification process is over pretty quickly. And if we look at the current during these 22 nanoseconds based on a charge of 10 million electrons, it averages around 70 microamps. And this is a value that we can measure fairly easily. By the way, not all light is converted into electrons. This plot shows the spectral response curve for our photomultiplier in two different ways, as quantum efficiency, which is an indication of the number of electrons per photon. It also shows the radiant sensitivity in milliamps as a function of the absorbed power in watts. If we take, for example, the quantum efficiency, we see that it varies quite a bit over the sensitivity range and has a maximum value of around 25%. The most important thing I want to point out is that it shows the photoelectric effect in practice. Above, say, 800 nanometers, the sensitivity rapidly drops off, and at 900 nanometers, it's only 1/2500th of the value at, say, 400 nanometers. So this is an illustration of the threshold frequency observed in the photoelectric effect, where a photon energy of around 1.5 electron volts or lower is not sufficient to effectively release an electron from the photocathode material. Okay, so much for the theory. Let's now look at the practical aspects. Photomultipliers are pretty expensive devices when bought new, and even second-hand, they're generally not cheap. On eBay, second-hand photomultipliers of the type I have here can cost anywhere between 25 to a few €100. But that's not all. To operate them, you also need a socket for the connector, some passive components to make the voltage divider, a high voltage power supply, and additional electronics to record the signals. And all of this can make light detection experiments involving photomultipliers expensive and complex, especially because you're also working with serious voltages in the order of a kilovolt.
Damn it! Stupid capacitor.
So how did I go about this? Well, I was actually a bit lucky. I found several surplus devices on Marktplaats for €100 a piece. However, these not only held a photomultiplier, they also contained everything else I needed to operate it. A protective and sturdy anodized aluminum housing, a special PCB with all the additional electronic components such as a socket, high voltage power supply, an electronic circuit that amplifies the output signal, and even a set of cables. On top of that, these also contained a little bonus. Inside the aluminum housing, I discovered a nice bandpass interference filter, a 20mm plano convex lens, and a polarizing beam splitter, which can all be useful in later experiments. Unfortunately, there were no data available on how to connect the PCB, and since I'm just a random chemist and not an electronics expert, it took me quite a bit of effort to find out how to connect these properly. But I think it's interesting now to discuss the PCB in a bit more detail because it taught me quite a bit, I guess mostly about how one can operate a photomultiplier properly. I found out that this PCB requires a power supply that can deliver both -15 volts and +15 volts with respect to a common ground level. And these voltages can be supplied to the PCB through the large screen connector here. The PCB also has two gold-plated connectors assigned K1 and K2, and after a bit of searching on the board, K1 turns out to be an input that can be used to control the high voltage of the photomultiplier and thereby its gain, and K2 is an output that contains the photomultiplier signal as a series of positive pulses. These little rings mounted on the board can be used to measure specific voltages and signals on the board and are assigned gain, ground and video. The PCB itself contains several key components. The first is a photomultiplier socket assembly for mounting the photomultiplier. This component is actually very convenient because it's not just a connector. Hidden inside is also the complete voltage divider circuit. The schematic of the socket shows that in addition to the voltage divider resistors, the last three amplification stages are connected to 10 nanofarad capacitors, and these are added to support the relatively large currents that can temporarily run in these last few amplification stages. With all the electronics inside the socket, this not only saves a lot of soldering and space on the PCB, it also means that there are just three external electrical connections needed, which are signal output, ground and high voltage. And it's these three connections that can also be observed on the other side of the PCB. The high voltage terminal is easily recognizable from the rather large gap to ground. The ground terminal is of course directly connected to the PCB's ground plane, and the anode containing the signal is directly connected to an AD817, which is a little operational amplifier IC. The second interesting component on the PCB is this tiny variable high voltage power supply. And I guess generating the high voltage very close to where it's used reduces the risks associated with external high voltage power supplies and cables. According to the datasheet, the C4900 needs plus 15 volts for power supply, which is how I figured out one of the supply voltages for the PCB itself. It can deliver a negative high voltage down to minus 1250 volts with respect to ground. And the high voltage level can be set by an external controlling voltage in the range between 0 and plus 5 volts. As you can see in the graph taken from the datasheet, the value of the high voltage output is linearly proportional to the controlling voltage, with minus 250 as a multiplication factor. And to stabilize the high voltage output of the supply, the PCB also contains a large high voltage capacitor of 47 nanofarads. Now, I don't want to go into every detail of this board, but just to outline how things are arranged, there is a gain control path that runs from K1 to the high voltage power supply involving an AD817 op amp, and this regulates the high voltage to the photomultiplier. And the high voltage is stabilized by the capacitor. At the other end of the photomultiplier, its anode is connected to an amplification path that inverts, regulates and filters the signal and then outputs it to K2. Now, I saw these boards for sale on both eBay as well as on Marktplaats, where they're still available at the publication date of this video. If you want to do some signal amplification of a photomultiplier output yourself, but you cannot get your hands on something similar, you can try the following. I found out that basically one op amp can do the job, which is shown in this schematic. If you were to connect a single AD817 like this to the anode, it can invert the negative pulses from the photomultiplier to positive pulses. At the same time, you can also amplify the signal level quite a bit by tweaking the values of the resistors R1 and R2. Also, it's a good idea to follow the guidelines on the AD817 datasheet regarding the use of additional capacitors to optimize stability and performance. So let's see if we can get this detector to work. Here is the setup I built. On the right is our photomultiplier assembly. I kept a 2mm aperture in front of the photomultiplier, but removed the interference filter, the lens and the polarizer I found inside the housing. The plus 15 and minus 15 volts and ground connections were supplied to the board by using two power supplies chained together. The gain is set using a third variable voltage supply on connector K1, and the signal output of the board is fed into a digital oscilloscope. Since a photomultiplier is really incredibly sensitive to light, normal indoor light levels will completely overwhelm it, and in fact you should never apply a high voltage on a photomultiplier under regular lighting conditions, because if you do, you can easily damage it. So you need to perform any experiments in extreme darkness, and this turned out to be quite a bit harder than I expected. I first tried placing it in a light-proofed cardboard box, but this was far from sufficient. In addition, I had to wrap the whole setup in several towels and also had to darken the room itself completely. And this resulted in conditions that were finally dark enough to do meaningful experiments. As a light source, here shown to the left, I decided to use a 520nm green semiconductor laser in non-lacing mode, connected as shown in this schematic. In non-lacing mode and at low current, it's basically a small LED which emits incoherent radiation. And when I operate this light source at a voltage of 2.7 volts, it's virtually impossible to see any light coming out of it. I tried to film the light output with a camera. At normal light levels I couldn't see anything, but in a dark room and with increased sensitivity of the camera, you can actually make out this tiny dim point. If I increase the voltage to 2.8 volts, you can definitely see some green light with the camera, but with the naked eye it's still very hard to see. And this very dim light source is placed at a distance of 200mm from the photomultiplier entrance without any lenses or focusing, just a small pinhole. I connected the light source to a function generator which allowed for modulating the light between on and off with a frequency of 1 kHz, and this is very useful because it allows us to directly compare the photomultiplier signal with light and no light being present. Okay, here is the setup again, closed up and in the dark. The light source is currently still off, so let's apply -1 kV to the photomultiplier. and here we go. We start to observe a signal consisting of individual spikes, and these pulses are detection events from the anode, and the signal has been inverted and amplified. But where do these spikes come from? Because, as just stated, the device is now in complete darkness, and it turns out that additional measures to further darken the room or the box have no effect. These pulses remain present. As you can see, there's actually quite a lot of them, and if we trigger the oscilloscope on these pulses, we measure on average about 300 per second. Since these are apparently not caused by light, why do we observe them? Well, it turns out that these are the result of so-called thermionic emission. These are electrons that are ejected from either the photocathode or one of the diodes, not because of light, but because of the effects of temperature. In general, metals contain so-called valence electrons, and these are electrons that are not bound tightly to a particular atom, and they're basically free to roam around in the crystal lattice. They make metals good conductors, but they cannot just leave the metal itself. What is holding them back is an energy barrier that they need to overcome to do this, and basically this is caused by a potential difference between metal lattice and the vacuum. And this energy barrier for electrons is generally referred to as the work function, and it has a different value for different metals, as you can see in the examples in this table. One of the lowest values in the table is actually found for cesium. Now, the distribution of energy of electrons inside a metal as a function of temperature can be described by the Fermi-Dirac equation. And at absolute zero temperature or 0 Kelvin, all electrons have an energy below the work function. So none of them can escape. But at elevated temperatures, for example at room temperature, there's always a fraction of electrons that has sufficient kinetic energy to overcome the work function barrier and leave the material. At relatively low temperatures, this fraction is very small, but with increasing temperature, more and more electrons are able to escape the material based on the thermal energy alone. The temperature-induced current that we observe is also described in the photomultiplier datasheet as anode dark current. At 25 degrees Celsius and at an operating voltage of -1 kV, the dark current of our photomultiplier is specified to be 3 nanoamps, which is equivalent to about 500 counts per second on the anode. But of course, this value is strongly dependent on temperature, as is also shown in the current plot that shows anode dark current as a function of temperature. Now notice that cooling the device down by around 25 degrees Celsius would effectively reduce thermionic emission by a factor of 10. So it might be a good idea to cool the photomultiplier down a bit in later experiments. For now, we'll leave it as it is and we'll start detecting the effect of light. For this, I'm first going to switch on the voltage modulation to the source to a level below which it emits any light, and this allows us to trigger on the positive flank of the light modulation, which is set to 1 kHz. Because the voltage level is currently too low for the light source to emit any light, we're now just observing the thermionic emission. So let's bring the voltage to a level that we know light is being emitted, but below what we can see with the naked eye. Okay, if we watch carefully, it's clear that we do detect way more peaks within the time span that the light source is in the on state. We do of course also occasionally still detect a thermal electron during the time the source is off, but currently that's a minority of all the detections. Now let's see what happens when we increase the voltage to a level where we can actually just see the light with the naked eye. Here you go. As you can see, our photomultiplier has no problem detecting this light. And now a vast majority of the pulses observed is indeed the result of light absorption. Here I increase the timescale by a factor of 2. If I increase the modulation to 2.9 volts, it's getting pretty crowded with pulses. And at 3 volts, things are getting a bit out of hand. We might even be saturating the photomultiplier here. Let's take a look at what individual pulses look like. We observe a rise time of around 20 nanoseconds and a fall time of around 110 nanoseconds, meaning that the half-width of the pulses is around 70 to 80 nanoseconds. And that's in fact quite a bit more than the value of the electron transit time inside the photomultiplier, which was specified to be 22 nanoseconds. But the latter value does of course not include the limitations imposed by the anode grounding resistance and the amplification electronics. So this is what single photon detections actually look like. We measure a short current pulse, which is the result of an avalanche of electrons initiated by the irreversible and quantized transfer of radiative energy upon a single electron. In the next video, I will do a few experiments involving very dim light sources and do photon detection with multiple photomultipliers, and we will try to observe a phenomenon called photon bunching. If you look at the situation where the light source is in the on state, it seems that these individual detection events are randomly distributed in time. But if you were to study them a bit closer, it turns out that this is actually not the case, especially when detecting incoherent radiation. Why that is will hopefully become clear in part 2. Thanks for watching.